Hello everyone. In this video, you will see a demo of a DDoS attack detection in the case of massive machine type communication slices in 5G. This demo is done in the context of the H2020 MonB5G, which aim to achieve zero-touch management in future 5G, beyond 5G and 6G network. And the demo is done by the NetSoft group of the Communication System Department of Eurocom. The demo objectives is to demonstrate MonB5G component to ensure zero-touch service management by detecting and mitigating DDoS attack in 5G, considering the case of massive machine type communication without human intervention. Before going to the demo itself, let me introduce first what are the main output of MonB5G project and the main ID defended by the MonB5G project to ensure zero-touch management in beyond 5G for the context of network slicing. So MonB5G consider an end-to-end network slices that are deployed on top of different technological domain composed by a radio access network, the transport network, and the cloud and edge part. Each technological domain is managed by its own orchestration and management tool, and MonB5G will provide the system that allow to introduce intelligence and, of course, using AI and machine learning in order to help these systems or this orchestration and management system that I call it assisted system, in order to take decision without any human intervention. And as you see in this figure, we have like a closed loop. So MonB5G introduced the element which is called monitoring system. The monitoring system objective is to do data collection from all the technological domain hosting an end-to-end slice, format the data, and aggregate this data. So the data will be provided and exposed to be consumed, but what we call an analytical engine. The role of the analytical engine is to train machine learning models, but also to run this algorithm, do inference in order to detect any anomaly or security threat as in this demo. Then this analytical engine will generate notification and alarms to a decision engine, which take the decision, which is based either on a policy provided by the slice owner or use inside it a reinforcement learning algorithm in order to take the decision. So decision making for the decision engine could be increasing, for instance, the resource block, the CPU dedicated for the virtual network function running the slice component, update route in case of transport network, or block traffic as in the case of this demo. So this is the high level picture of the demo you will see in this video. It represents a slice where we have shared component here, which is the core network and radio part, which is composed by IoT devices. We assume that there is a high number of IoT devices, and all the IoT devices are generating traffic, which follow a normal traffic beta distribution 4, which correspond to the specification that are provided by 3GPP in this document. So what is the role of the monitoring system here? First, the monitoring system will monitor the number of attached requests received by this element, which is the IMF. And this data will be formatted and provided to the analytical engine, which will do analysis using machine learning algorithm. And this analytical engine will detect if this is abnormal traffic or normal traffic. Normal abnormal traffic, which means that there is an attack ongoing on this IMF, which is the authentication, authentication and mobility function of 5G. Then the analytical engine will generate a list of suspected UE to be malicious. Then this D will do the mitigation by detaching these UE and blacklist them. So the information will be enforced through the IMF in order to detach the concerned UE and blacklist them. The analytical engine run a gradient boosting technique coming from machine learning to classify traffic and hence detect abnormal one. So you have this picture here, this figure, which show traffic generated from IoT devices, and all traffic that are inside this area are considered as normal traffic, but all the traffic that are outside this area and close to this green line, which is the anomaly interval detection, all this traffic will be considered as abnormal. And in this case, the analytical engine will send output to D containing the list of user equipment with an unsuggested probability that they are malicious. So for the demo and to implement this, so all the three components of MonB5G are implemented using Python code. And the IE, as I said, is using this gradient boosting machine learning algorithm. And for the 5G component, the IMF and UDM, which is the database of user equipment, are based on OpenAir interface, which is, as you know, an open source implementation of the 5G protocols. Here we are using the core network part. And for generating the traffic and of the IoT devices, and to be as close as possible to the reality, because we need to generate a high number of attach, we use my5G run tester, which is an open source tool that allow to emulate 5G traffic, and particularly G Node B and user equipment traffic, following the standard, which means that the IMF will see a real attach that comes from these devices using the NGIP protocols, and the IMF will send the information to the monitoring system, and the loop is closed, and the IMF then send the detach if some user are detected as malicious, and including the UDM, this user as blacklisted to be forbidden from future access. Time now for the video, which will be presented by Radwan Nibusha, who is the former member team of the NetSoft group.
Now it's time for a live demonstration of our system. So you can see here on the right we have the logs of the analysis engine, the decision engine, and on the bottom right our command line where we will run our commands, and on the left we have the logs of our IMF component from our core network. So we will start by sending this request, which simulates an event of length 20 seconds with 30 user equipments. So we run it. You can see on the left there are some registrations that already happened. You can see on the analysis engine component some logs on data being inserted. And you can notice that for the decision engine didn't receive data yet, because the end of the event hasn't been detected yet. You can see that the event has ended, success, but that decision engine didn't process data yet because the other components didn't detect the end of the event yet. You can see on the AMF logs that all the equipments have been registered. And you can see also on the analysis engine some updates that now some detection values have been calculated. And you can see on the decision engine, some decisions have been taken. Some MC values have been added to the blacklist. You can see, for example, the devices that got a detection rate of 25% haven't been blacklisted. And you can see on the logs of the AMF that they have been deregistered, that their state has been changed to deregistered. Okay, now we will simulate another registration of a device. So this time we will register this device with MSEN31. It hasn't registered before, so in this case you can see that the registration has been successful. And it's now registered, as you can see. Now we will try to register a device that has been blacklisted in the past. Let's try, for example, 25. You can see that the AMF has received the registration request, but that is still in the deregistered state. And if we look at the logs of the AMF component, we can see that a registration reject has been issued when the MC has been found in the blacklist. You can see. So the malicious device can no longer connect to and register to the network.